Hi, I'm Sammy. I'm one of the contributors for the Daft open source project, and I'm really excited to present it to you today. So, a little background on us. I'm Sammy Sidhu. I'm the CEO and co-founder of Adventure Computing, the company behind Daft. My background is in high-performance computing and machine learning. I have a dozen or so patents and publications in the field, and I've worked in self-driving the last decade, working on problems dealing with image and LiDAR data handling. I was a chief architect at DeepScale, which was acquired by Tesla, and I've worked at places like Lyft, Level 5, and Toyota. And this is Chia.
Yeah. So hi, I'm Jay. I'm the CTO at Adventure Computing. I led a lot of machine learning infrastructure at Freenome, which is in biotech, and at Lyft Level 5, where I met Sammy. And I was in the computer science program at Cornell, and now we're building Daft together.
Yeah. Cool. So, what is Daft? Our title slide said it's the Python distributed data frame for complex data. That's a lot to unwrangle. So, let's do it word for word. So, Python. Daft is built for the Python ecosystem. It uses native Python objects and functions. If you know Python, then Daft will be really easy to pick up. It's distributed. Daft uses partitioning to do out-of-core processing on your local machine, but it then can easily scale to the cloud on dozens or hundreds of machines after. Daft is built using the data frame abstraction. If you use something like pandas or polars or Dask data frames, then the API will be very familiar. Daft follows a lot of the same principles and is as easy to use. Also, Daft is for complex data. Now, what does that mean? At a high level, complex data is just anything that's not tabular, things like images, video, audio. But I really want to dive in deeper and define what complex data is. So, what's complex data? So, I believe that data kind of lies on a spectrum between primitive and complex. If you've programmed before, you're familiar with the concept of primitives. These are the atomic building blocks you use to build your program. Things like integers, strings, floating point numbers, and Boolean values. Oftentimes, these are really powerful concepts that can represent things like someone's age or birth year or someone's name or a constant like pi. But we usually chain them together to form higher level abstractions, things like objects or structures. In data systems, we actually combine these primitives together to make structures like latitude and longitude, which can encode the location on Earth, or a person, which can combine a string and a number to compose someone's name and age. These structures are actually more complex than a primitive. They are composed of more primitives, but they also encode something with semantic meaning. Latitude and longitude encodes a place on Earth, which has certain constraints and logic that it requires. And a person also has certain constraints, like a person can't have a negative birth year, or a name has to be formatted a certain way. Now, what about something like an image? How would we think about representing this? One approach could be that we make a structure and we encode things like the height and the width. And for the data, we can actually just have a sequence of integer pixel values. So this is a decent approach, but one downside of this is that we couldn't do things like compression or do things like store things with different image formats. One thing I find really interesting is that one thing that goes around is that images are unstructured data. I disagree with that because if you actually look at this image, it's highly structured. It has a height, a width, and it has a fixed amount of data pixels. It's a tight grid. So why do people call it unstructured data? I think people call complex data unstructured because, like unstructured data, it requires a lot of processing to extract meaningful value. But really, we should be calling this complex data. Unstructured would be something more like a directory full of JSONs with different schemas for each one, not something like an image. So let's go over what makes data complex. Number one, if it's composed of more primitives. This image that we show here of the astronaut on the horse can contain over 1 million pixels, 1 million different primitives. Extracting value out of that or generating something like that actually requires quite a bit of computational power. And sometimes it can require something like an accelerator, like a GPU. It can require domain-specific semantics. Something like latitude, longitude is only 2 floats, but it can require a lot of specific logic for it, especially if you're trying to compute the distance between 2 different places on Earth, or do something like an intersection test. The Earth is a sphere for most people. And if you want to do logic, you actually use the curvature of the Earth and sometimes use it for different regions. There's tons of extensions for this, but generally it's a little bit more complex. Or it could be hard to represent. At first glance, a video is just a sequence of images, but if we represented it that way, we would explode the amount of data we use. Oftentimes, videos are represented by codecs, which are usually like a sequence of still frames and then diff frames essentially from that, which means it's great if you want to move forward in time in a video. But if we want to enable things like random accessing or move backwards in time in a video, it becomes quite difficult. So if we wanted to do that, we would have to represent data in a way that would make it easy. Cool. So now we have defined complex data. Let's kind of go over the landscape and see what tools we can use. Okay, if you are only working in primitive data, you're in luck. There's lots of really good tools for that. A common user interface for primitive data is something like SQL. And if you're using SQL and you want to do large-scale data analysis, you have things like Snowflake, Google BigQuery, and the new and hot DuckDB. These are really great at expressing queries if you're doing things like standard SQL aggregations and data processing in that regard. But once you need a little bit more flexibility, using an engine that supports user-defined functions or UDFs is really powerful. One engine that I found really powerful is Spark SQL, where you can define user-defined functions in Python, register it, and then call it from SQL. In the example we gave about computing the distance between 2 points on Earth, you can write that as a Python UDF in Spark, register it, and then use that in SQL, which is really powerful. If you need more flexibility, you have something like tabular data frames, which is like pandas, which I'm sure many of you are familiar with, and polars, which is like the new and hot data frame library. These are really powerful for expressing compute. You can run almost any arbitrary Python function on your data frame. But the part that's limited is the data types that it can represent. You're still limited to essentially what's supported by most SQL engines. Now, if you're dealing with the data that we're talking about, complex, images, video, audio, all the stuff we've been going over, what's kind of the tools you would use? And the answer is you're kind of on your own, and you kind of have to build something from scratch. In the times I've worked in self-driving, we've had to kind of build out bespoke systems for each application we're targeting. You normally would encode your application and build your logic using libraries like Pillow, NumPy, some kind of job queue system, and deploy it on an infrastructure like Kubernetes. For data storage, you usually define your own protocols and put them in something like Parquet and store it in S3. And this usually requires a large team to maintain and build, and I think is a huge barrier to entry for a lot of people to wrangle complex data. And that's why we built Daft. We want to bridge the gap. Daft can represent all the data types that we talked about that are primitives, things that polars, pandas, and Postgres can handle, but can also unlock the potential for wrangling complex data. So you can, in a single data frame, have things like integers, strings, normal numbers, and also have images, video, audio in a single data frame and do processing on it. So what does Daft come with? It comes with a familiar data frame interface. If you've used pandas, Daft will be really, really easy to pick up. We have an expressive typing system. We actually do Daft in a completely lazy logical plan. What that means is that as you're writing Daft, we can actually infer types and build essentially a schema for every data frame using the composite types of primitives and the data types that you're using natively. So if you make your own data class or your own Python object, we can represent that as a type. We have really powerful Python native UDFs. If you have your own Python objects and you want to run your own functions on them, you can run them easily on Daft. We also support stateful UDFs. If you have a machine learning model with state, or you want to use something like batching in your model and use a GPU, you can express it as a stateful UDF and deploy it on Daft. And finally, we're distributed. We leverage partitioning to do out-of-core processing on your machine and parallel processing in the cloud. It's a simple one-line change on your laptop to go from there to the cloud. And now it's time for a live demo.
All right, let's do a live demo. Always fun. So in this demo, we will be going through a simple example of how you can use Daft to go through the open images dataset and find the images that are the most red, right? We just want like the reddest images and show that, maybe save that, and maybe we can relabel it and stuff like that for a machine learning use case probably. So let's start off with just defining this one flag distributed equals false that I'm using in this notebook to run everything on my local laptop. We'll go through what that means in a bit. And later on, we'll revisit this and show how we can use Daft in a distributed fashion on the cloud. So by setting this flag now, distributed equals false, we can run this and start loading the images from a remote storage, right? So in this case, we actually have all our images saved at this URL somewhere in AWS S3. And all we have to do is say, hey, Daft, load a data frame from these files. And since we're not running in a distributed mode, we're going to hit this line of code, which will limit the number of rows to just 100, just for the sake of this demo, so that we can process everything in a good amount of time. And so we will print the data frame, and what you'll notice is that Daft will say, hey, there's no data to display right now, right? The data frame hasn't been materialized, and that's because, like Sammy said, Daft is lazy. So until you actually tell Daft to compute and materialize your data, it's not going to. But what Daft can do is that it will actually already tell you what columns are in your data. So these are all the columns we have, right? There's a size column, which tells us how large each image is. And then this other name column will be important because it's the actual path, the URL to the image, essentially. And so let's go ahead and just run some filters on the data, which is really common whenever you first wrangle a data set. You want to filter just for the data you want. And I'm going to run two filters to filter the size for everything smaller than 300 kilobytes and everything larger than 200 kilobytes, right? Again, Daft is lazy. So by running this filter, you're not actually running any computation. What you're doing is you're enqueuing these operations in a query plan. And so you can view this query plan. It's really powerful. You can view it. And you can actually see here that there are these two filters, each one corresponding to these two commands we just ran, right? This one does a filter for everything less than 300,000. This one does a filter for everything more than 200,000. What you'll notice is that, hey, actually doing these two filters one after another is really inefficient. You have to go through the data frame twice to do this. And it would be much more efficient if you could combine these filters and do it in one pass. And that's the good news, is that Daft actually has a really powerful query optimizer that will do this optimization for you at runtime. So to view the optimized query, we run the same explain operation with a show optimized equals true. And now you'll see that there's actually just one filter, right? Daft has kind of combined and fused the filter operations, and now it performs both the filtering for more than 200K and less than 300K in size. So that's really powerful. And let's actually go ahead and run this plan right now, right? So the order of operations of this plan is going to scan some data. It's going to apply the limit that we defined, a limit of 100 rows, and then it's going to filter the data set. And so to run this data frame, you just call .collect. That will materialize your data frame in memory and run the entire plan. And we'll see that we actually only have 16 rows after running the filter. And all these columns here, and the sizes are all now between 200,000 and 300,000, which is amazing. That's exactly what we wanted. And we have this name column, which actually is the only column we need. Everything else is kind of just metadata. So let's go ahead and just prune this data frame down to just the name column. We do that with df.select, select the name column, and let's show 5 rows of the data frame. And awesome. Now this is the data frame we're going to work with. It's just this name column. Cool. Now let's start talking about complex data. That's what Daft really excels at. So with this name column, what we want to do now is start pulling images down from these file paths, right? To do that, we can first transform these strings into URLs by concatenating this S3 prefix and just doing a string concat to the name column. And that gives us S3 URLs. And then now we can just treat each string as a URL and call a download method on it. And this is where it gets really powerful, because when you think about it, a URL is just a string, but it has a semantic meaning of pointing out to some remote data that we want to pull down, right? So Daft allows you to interpret this string as complex data and download the data. So if we collect the data frame after creating this new column called image with this expression, we now see that we have bytes in our column. Amazing. We're now pulling bytes with a single line of code from these URLs, right? And now, the bytes aren't that useful. We need to parse them into images. So what we can do is we can define a simple user-defined function, or UDF, in Daft. And so this function is called bytes to pill. It converts bytes to pill images. And we're going to tell Daft that, hey, this function will require 2 CPUs to run. Right? This is a resource request. We can also request things such as number of GPUs, for example, if you're using GPUs. And then we'll tell Daft that, hey, this function returns a pill image. And then the function is super simple. It just iterates through the bytes column that we're passing in, creates a pill image, and resizes it to 256 by 256 in height and width. Super simple function. To run a UDF on your data frame, you just run it on your data frames column just like this. Run the bytes to pill function, run the bytes to pill UDF, on your image column. And we're just appending back to the same image column. So we're just replacing the bytes image column now with a pill image. And that's what you get. So now we have the URLs on one side and the images on the other. Cool. Now let's start doing some magic and pull out some of the red pixels in these images. To do so, I've defined this magic red detector. You don't have to know how it works. Just know that the magic red detector will take in an existing image, and it will output a new image, which is a mask of where it thinks all of the red pixels are. And to run this magic red detector on our column, all we need to do is call .apply. Right? This line says, apply my magic red detector on my image column and create a new column here called red mask. And so let's run this. And beautiful, it looks like our red mask is working. This airplane like stripes on the wing, some chilies in this dish. This red bag is like really activated. And so now we maybe want to sort by how many red pixels there are, right? So again, define a super simple function to sum up all the bright pixels in the mask. And then I'm going to sort by this new column that I've created called the number of pixels that are red. And we're going to sort it by descending order. And so we'll see that the red bag now is ranked pretty high. And everything else that doesn't really have red pixels are kind of ranked at the bottom. Cool. So we've just ran, on 16 rows locally, just on this data frame and experimented locally. What if now we wanted to run in the cloud and run on much more data? So we can do that simply by connecting Daft to a remote cluster. So I'm going to go ahead and clear all the outputs here, and let's rerun our notebook. And now I'm going to switch this flag to distributed equals true and show you some of the code that's necessary to connect Daft to a cluster. And so we're using Ray here, which is a distributed computing framework. This is initializing the Ray cluster, which I have set up already remotely, and I have a proxy locally. And in order to tell Daft to use this cluster for execution, all you need to do is call this one line of code, set runner to Ray, and give it the address to the Ray cluster. And now Daft will actually run remotely on the Ray cluster, right? So exactly the same code you call from files. We're going to load all of the data from our images again. In this case, since we're running in a distributed fashion, this flag is true. So we're going to limit our data set to 10,000 rows instead of 100. And we're also going to repartition our data set so that now we have our data frame is actually 64 partitions that we can now process in parallel and do things really efficiently. So let's go ahead, and all the code from here on is exactly the same, right? We're going to go ahead and filter our data, these explain operations, and now we'll collect the filtered data frame. So this is now executing on the 10,000 rows, and we'll see that after filtering, we now have 2,000 rows instead of the 16 that we originally had when we were running just locally. And so now same thing, filter we'll just get the name column, download the URLs. And so now this download operation is running a download on all 2,000 URLs. And notice how fast it ran because it's running on a remote cluster with many, many more CPU cores. And it can run these partitions in parallel. And so we're going to go ahead and load the bytes into images. These are now running on the remote cluster. The remote cluster now will also do the magic red detector for us. So it's running the magic red detector on all 2,000 images. So it'll take a little while to run. And so these are all the images from our new larger data set. So some of the images are different, like this one here with like red seats, a red car. We're going to tell Daft now to run the counting of the pixels on all 2000, and now we'll sort based on the count of grid pixels. Ignore all these warnings. NumPy and Pill don't get along for some reason. But yeah, now that we have way more images, a lot of the images are actually kind of very red. There's one right here with watermelon on the red background. That's our reddest image out of all of our 2000 images. These flowers, watermelons, looks like watermelons in general are pretty red. I think these are tomatoes and a Ferrari. Yeah, and so now we have 2000 images all sorted by how red they are, right? And they're super simple to do in Daft just by defining all these custom functions on pill images. And that's it for the demo.
Yeah, thank you. And yeah, just to recap, Daft is a data frame library to kind of bridge the gap between primitive and complex data. Where we have a data frame interface, we have an expressive type system, as you saw, that can work with both types of data. And we have powerful UDFs that can do things like detect red, download URLs, I guess, and whatever else you can pretty much think
run
of.
Machine learning models.
Run machine learning models.
Yep.
We're distributed. As you saw, it's pretty much a simple line switch to go from your laptop to the cloud. And yeah, we're Daft. You can find all of this at getdaft.io. So we hope you guys get Daft. We're hiring for people who have backgrounds in databases, compilers, distributed systems. Come chat with us. And our emails are right there, Sammy and Jay at adventurecomputing.com. Thank you.
Thank you.
All right, now I've got to find the. How do you
stop sharing? And yeah.
Cool.
Oh, hey, we do have one question in there. Patrick, from Patrick.
Oh.
Yeah, from Patrick, only the resized photos are stored in memory in the Daft data frame. Is that right?
That's correct. So what we do is we have the bytes stored in memory. And then when you do the resize, the decompression, which gives the full memory, and then the resize, only the resized memory photos are stored in memory, and then the former bytes are garbage collected.
Yeah, and something really important to note is that, let's say you have two functions, and the function before loads in an unresized pill image, and then you run another function to resize it. Daft performs these optimizations that will fuse these two together. Right, so you don't actually have to materialize the really big unresized image in the middle, because Daft is smart enough to fuse them.
And it also supports out-of-core. So because we didn't have any sorting or anything beforehand, if I only had, let's say, 100 gigs of RAM in my cluster, but a terabyte of images, Daft will automatically do it in Windows and actually store the resized images in memory and spill it over to disk.